How you doing, physics fans? Today we're going to talk about free body diagrams. Now, free body diagrams are very useful whenever you're applying Newton's second law. So when you recognize a problem that you need Newton's second law in order to solve, what you want to do is start figuring out and drawing your free body diagram. So we have a few steps and we're going to talk about them on how to do those. So the first step is isolate the body. So whenever you're applying Newton's second law, you want to isolate your body. Look at your picture, your drawing. You have different objects. You may have pulleys. They may be on inclines, doing all these different things. Look at one body at a time, isolate that body, and draw it by itself. Next thing you want to do from that isolated body is you want to draw and label all external forces. Now, we have a great acronym to help you remember all the potential forces that could be applied to an isolated object. The acronym that we use is WANT-F. And what those letters stand for are weight force. You could have an applied force, you can have a normal force, you can have a tension force, and you can have a friction force. So those are the forces that we work with and talk about when we're applying Newton's second law. The next step is choose a coordinate axis and direction for positive rotation. So you always want to choose a coordinate axis. Now we'll talk a little bit about ways that you can pick a coordinate axis that will reduce the amount of trig you have to do and the difficulty of the problem. But generally you want to always identify a coordinate axis and ensure that your axis is consistent between multiple objects in your problem. Direction for positive rotation. Now, we'll talk a little bit about that when we get into the rotation block. So right now we'll just remember when you get to rotation, you will also have to choose a direction for positive rotation. Right now we won't talk about that one. And then last is include critical angles and dimensions. So you want to include any angles that are going to be necessary for you to solve the problem. And then when we get to rotation, critical dimensions and different dimensions in the problem that are going to be critical to solve that problem. So let's use an example. So right now you can see I have a box that's on an incline. That incline is inclined at angle theta, and let's draw a free body diagram of the block and the forces acting on that block. All right. So first thing I want to do is isolate the body. So I've isolated my body. After I've isolated my body, I want to orient it in the same general direction that it is in my picture. So it's on an incline, so I'm going to put it at an incline about right here. Right there. All right, so I've isolated my body. Next is draw and label all external forces. So in this case, I have a block. Is there a weight force on this block? Absolutely. I have a weight force. I can apply it to the center of mass of my object, and we'll go ahead and represent that, of course, as a vector directed towards the center of the Earth, and its mass times the acceleration due to gravity near the center of the Earth. Next is an applied force. In this case, as I'm looking, I don't have any applied force on this object. So there's nothing pushing on it. There doesn't have a force in the picture. There's not somebody applying a force there, so I don't have an applied force. Is there a normal force? Absolutely. Since this box is sitting on a surface, I have a normal force that originates from that surface. It's 90 degrees to the surface. And again, I draw it on the bottom of wherever it's being applied right there. So there's a normal force on that body. Next, there's a tension force. So there's no tension force here. There's no rope. There's nothing pulling that box. So I'm going to say that there's no tension force on this block right now. And then last, there's a friction force. So when I look at this block, it looks like it wants to slide down the ramp. So I'm going to have a friction force that's going to keep it on that ramp. So the friction force is applied onto the ramp. So it's on the bottom of that. It's on the bottom of that block wherever it's touching, and it's opposing impending motion. So this thing wants to slide down, and the friction force is keeping it from sliding down. Let's go and label that friction force, and I know it's a static friction force. Now, we haven't necessarily talked about, or you may have not talked about friction forces yet, but you will get into those very shortly. All right, I went through my WANT-F. I've identified all my forces acting on the object. Now I want to go choose a coordinate axis and direction for positive rotation. So my coordinate axis, as I'm looking at this object, I'm going to draw a coordinate axis that's at the same incline as my ramp. And the reason I'm doing that is because if you look at my normal force and my friction force now, the normal force only has a y component. The static friction force only has an x component. Awesome. So now I know that those two forces are only going in the x and the y, or in the y and the x respectively. I don't have to break those into components, but I do have to break my weight force into components. So let's go to the next step and we'll talk about that. So now I want to include critical angles and dimensions. So obviously there's a critical angle because I know my weight force is acting both in the x and the y direction. And you can talk to your instructor about this one, but I know that that angle off of the y-axis, as drawn, is the same angle as the incline. Ask your instructor to show you through similar triangles why this is true. You can always apply this when you look at a box on an incline. You know that this angle from this y component, or from the y-axis, is always going to be that angle theta as drawn there. So that concludes our free body diagram video, and I will see you next time. You know what? That was way easier.